In this last video, we'll get to learn about the divergence theorem, which is the other great result of vector calculus next to Stokes' theorem. Recall that Stokes' theorem related a line integral of a vector field around a closed curve to the surface integral of the curl of that vector field across the surface whose boundary was given by that closed curve. The divergence theorem will relate the surface integral of a vector field to the triple integral of the divergence of that vector field. The surface will be assumed to be a closed surface, and the triple integral will be evaluated over the region that is enclosed by that surface. So let me state the theorem, the divergence theorem. So let E be a simple solid region in space, and let S denote the boundary of that region. So the boundary surface of E. Now, with a positive outward orientation. Meaning that we have some solid region in space. So E is that solid region, and its boundary, the surface, that is the boundary of that solid region. Let's call that S. We'll have an outward orientation, meaning that the normal vectors point outward. Okay, and then if we have a vector field, so let F be a vector field whose components have, again, continuous partial derivatives on an open region in space which contains E, which contains this solid body with its boundary, then we have the following relation. So the surface integral of this vector field across that surface S, that is the boundary of E. Again, we may use this notation that the boundary of our solid region E would be the surface S. This will be equal to the triple integral of the divergence of our vector field over that solid region E. So that is the divergence theorem, which is, as I said, the other central result from vector calculus. So it is a very important result. Now, let's see an example. So let me show you an example. So let's find the flux of the vector field, the surface integral of the vector field f of x, y, and z with components z, y, and x over the unit sphere given by the equation x squared plus y squared plus z squared equals 1. So let's compute this flux using the divergence theorem. Okay, so set up the right-hand side of the divergence theorem for this particular vector field and this surface, and evaluate the flux via that way. Pause the video and input your answer below. Okay, I hope you paused it and have found that this surface integral, this flux will be 4 pi over 3, and the reason is that when you take the surface integral of this vector field, which, remember, had components, so z, y, and x, and you want to compute the divergence of that vector field, well, you'll just have to take the partial derivatives of each component, of the components with respect to x, y, and z. And when you do that, of course, the partial derivative of z with respect to x gives you 0. The partial derivative of y with respect to y gives you 1. And the partial derivative of x with respect to z gives you 0. So overall, this divergence is equal to 1, to the constant 1, at every point in space. So when you write down the divergence theorem and you want to compute the triple integral of the divergence of this field over the interior, the solid region that is enclosed by the unit sphere, that is the unit ball, then what you are doing, so let me continue that equation over there, what you are doing is you are integrating the constant function 1 in this case over that solid region that is the unit ball. So over the region where x squared plus y squared plus z squared is less than or equal to 1. Okay? So, and this is just the volume of that ball, is the volume of that solid region, the volume of the ball of radius 1. So that will give us just 4 pi over 3 times the radius cubed, but our radius is just equal to 1 now, so it's 4 pi over 3 for that reason. So you can see how using the divergence theorem and finding the divergence be a constant function gave us this surface integral, the flux, almost immediately as the result. Okay, so that was a quick example. Now, what if this surface, I mean the solid region, is not has a hole in the middle? So what if the solid region looks something like this, where you have two surfaces, and in between the two surfaces, that's the solid region we are interested in, and that's our solid region. How should we choose this outward oriented normal vector then? Well, for the outer surface, it would be the usual outward pointing normal vector, but for the inner surface, we should, for that surface, that which is also the boundary of our solid region, the outward pointing normal vector would be pointing outward from the region that we are interested in, which is between the two surfaces. So it would be pointing towards that cavity, basically. So that's something to keep in mind when evaluating, when using the divergence theorem. Now, another thing we should mention is that this divergence theorem can be used to understand what the divergence actually means. So if we have a certain fluid with the velocity field given by some vector field, f of x, y, and z, then this velocity field will be actually giving us the rate of flow per unit area. Okay, and what we can do is we can take a point in space, p naught, and draw a little ball around it. I will exaggerate in this drawing. So take a ball around, centered at p naught, with some small radius a. Okay, for this small ball around p naught, the divergence of this vector field will roughly be, well, for every point within that ball, for a continuous vector field, so the continuous divergence, it will be roughly the same as it is at P naught. So when you write down the divergence theorem for the surface integral of V across the surface of that ball, the sphere of radius a centered at P naught, so let's call that sphere SA. What you'll find is, well, it is, by the divergence theorem, equal to the triple integral over that ball BA of the divergence of V, the vector field V, but that's approximately equal to the divergence of V at P naught integrated. So that would be having this divergence, a constant that we can factor out of the integral, and then we are left with the triple integral over that ball of radius a centered at P naught. And of course this approximation gets better as we take the limit better and better as we take a, the radius, to get to be smaller and smaller, and in the limit we actually have an exact relation. We will exactly obtain the divergence of our vector field at the point P naught if we take the limit of 1 over, well, the volume of that ball of radius a, so that's 4 pi over 3 times a cubed, times the double integral of V across that the surface of that ball, the sphere SA. So we take the limit a goes to 0. So the result is that the divergence at a point is this limit of the flux of the vector field across a small sphere around that point divided by the volume of that sphere as the radius goes to 0. Okay, so this gives us an intuitive understanding of flux, because basically what this equation says, that the divergence of V at P0 is the net rate of outward flux per unit volume. It's because we divide by the volume at P0. Okay, so this is why it's by the name divergence is given to this quantity. Okay, and it means that if this divergence is positive at a certain point, then the net flow outward near that point is positive. So we have something that can be regarded as a source for that vector field. And if the divergence at a certain point is negative, then the net flow is inward, so near that point. So we may think of that point as a sink in that case. So let me show you an image in which we have a vector field where at points, certain points, we have longer vectors coming in than the vectors leaving that point. So for example, right here, we have a point into which we have, so let's call this point P naught, where we have longer vectors coming in than the vectors leaving it. So there is a net inward flux. So for that point, the divergence of our vector field would be positive. It acts like a would be negative. So it acts like a sink. Okay, because there is more stuff flowing in than stuff flowing out. And for a point such as this one, well, such as this one, let's call that point P1, you can see that the vectors going into that point are shorter and the vectors coming out of that point or near that point are longer. So for this point we would have the divergence of the vector field be positive, so it acts like a source and more stuff is coming out of that point than the amount of fluid or volume of fluid that flows in. So that's the idea and that's the intuitive meaning of the divergence. So I hope you enjoyed this video, and this is the end of the lecture and these videos. I hope you enjoyed them, and I see you next time in class.